Hey everybody, this is going to be a quick walkthrough of example 2 that we didn't get to cover last night from chapter 9, section 3. So this is, in the textbook, it's page 463, once again, chapter 9, section 3. This was the last example that we didn't quite have enough time to cover in class. Section 3 was on confidence intervals for variance and standard deviation. So in this problem, that's exactly what we're going to be able to find. The problem, they give you a table, 12 randomly selected 6-year-old Chevy Corvettes. And they want us to come up with a confidence interval for the population variance and standard deviations, or excuse me, a 90% confidence interval for the variance and standard deviations of these 6-year-old Corvettes. So there's table 4. It's just 12 values, 12 random prices. And then below that, I have the information we're going to need for the problem, how to calculate the lower and upper bounds of your variance and or your standard deviation. Remember, variance is sigma squared, standard deviation is sigma. So we'll have to, this gives us, this gives us the sigma squared value. We'll then take the square root of it to come up with the sigma value. As you can see, that's what this note is at the bottom I've highlighted. To find the confidence interval about sigma, take the square root of the upper and lower bounds. So we always have to remember to do that at the end. First step here, I just have our information that we were given, given/found. The standard deviation of the sample, you would have to calculate that, once again, via Excel, StatCrunch, Minitab, whatever your weapon of choice is for your statistical analysis. But I would not expect you to calculate that by hand. That would be rough. We're looking for a 90% confidence interval, and our sample size is 12. That's just given in the problem. And since our sample size is 12, our degrees of freedom would be 11. So looking at our equations, we have n, we have s. Basically what we need now is our chi-squared values. So we're going to calculate our chi-squared alpha over 2 and our chi-squared 1 minus alpha over 2. It's just the tail values, because we're looking for that middle 90%. So we have those 5% on either side. So our lower bound chi-squared is going to be chi-squared 0.05, and our upper bound chi-squared value is going to be chi-squared 0.95. And then we just go to table 8, use degrees of freedom, go over to your chi-squared value, your 0.05, your 0.95, and then get the values from the chart here. So I got 19.675 and 4.575. Once again, these are not, remember, the chi-squared chart's very different than our normal distribution chart and even our t-squared chart. So our numbers are quite different. They don't add up to 1 anymore. So yeah, from there, it's pretty much just plugging in. So we have our lower bound of n minus 1 times s squared over chi-squared alpha over 2. We just plug our values in and we get a big old number there, almost 4 million. And then going through with our upper bound, we do the same thing. The numerator is the same. The only thing that changes is the denominator, the chi-squared value we get there. And that gives us roughly 16.5 million there. So keep in mind, those are not the upper and lower bounds of our standard deviation. A quick glance would hopefully prove that that wouldn't make any kind of sense. Thinking that if you did, because our values here are only in the, roughly tens of thousands, 40,000, 30,000, probably, I don't even think they get low 40s to high 30s. So having a standard deviation of 3 to 16 million doesn't really make any sense. But if we go ahead and root those, take the square root of each of those values, we end up down here with giving us a lower bound of 1,955 and an upper bound of 4,055. So what that tells us is we are 90% confident the standard deviation of the population is between those values. It's between 1955 and 4055. So that's what that tells us. And then, so that would give you, like I said, that's how you would calculate a confidence interval for a sample standard deviation. Alrighty.